Hi, this is Gordon Parker from Michigan Tech, and in this video we're going to look at stability analysis using the Routh array. So consider that we have a transfer function, could be closed loop or a plant transfer function, that looks like this. It has some numerator polynomial n of s and a denominator polynomial f of s. And of course we call this one the characteristic equation. And that's really the focus of this video. And we know that the roots of f of s are also called the poles of g of s. So we'll typically use those two terms interchangeably. Most of the time I'll just call it poles of g of s or poles. And we also know that if all the poles of g of s are in the left half plane, then our system is what we call Bibo stable. It means that for any bounded input, we know that the output will also be bounded if all of our poles are over here in the left half plane. If there's any on the imaginary axis or in the right half plane, then we know that the output will not be bounded for all bounded inputs. Now, the types of systems that we're going to look at here are things like this. So a nice, easy numerator, but let's say that we have this in the denominator. 5s squared plus 7s plus 9. So a fourth order system. So there's 4 poles to this system, and if we wanted to analyze its stability, we could certainly just use some sort of a root solver. We could use MATLAB or any number of the calculators that are out there, figure out what the roots are, look at them in the complex plane, and make some judgment, make some determination about stability. But let's say that you have a g of s that looks like this. So I'll take the same transfer function and make one little change. And what I've done is I've just replaced the 3 in the s cubed term with a k. And so now if the question was, determine the range of k for stability, well, a root solver would work. You could sit there and loop through a whole bunch of values of k to sort that out, or you could use the Routh array, which will be a little bit cleaner in some ways. So hopefully that gives you some motivation, and let's have at it. So let me just articulate the procedure first. The first thing that you want to do is extract that characteristic equation. And I'll just abbreviate it as this. So maybe you're interested in just the plant's stability, so you grab the denominator. Or let's say you have the block diagram of some closed loop system, some control system. Well, then you have to sort out the block diagram, get your closed loop transfer function, and then extract out the denominator. But get your characteristic equation that you're interested in. And then you form the Routh array. And here's what a typical Routh array would look like. Over in the left column, there are some labels, and these have to do with the polynomials of the characteristic equation. And then you have values in this Routh array, and I'll just use asterisks to denote a whole bunch of values. Maybe it looks something like that. And maybe we have another column here too. Okay, so you form this Routh array, and we'll go into how you do that. And after you form the Routh array, you look at that column, and that column alone is what tells you the stability of the system. And let me go to another page to write down how you analyze that first column. So the third step is analyze the first column. And we have the Routh stability criterion, which goes like this. So your system, your characteristic equation, is stable if and only if all the elements of that first column have the same sign. So I'll just abbreviate that description like this. Stability, all elements of the first column have the same sign. Okay, so it's sort of a binary check. We can determine whether or not the system is stable by just looking at the signs. And then we have the Routh-Hurwitz criterion, which goes a little bit deeper. And it says that the number of poles in the right half plane is equal to the number of sign changes of the elements in that first column. So I'll abbreviate it like this. Number of right half plane poles is equal to the number of sign changes of first column elements. Beautiful. And that's really the one that we're going to use because that's a stronger condition than the other one. So let's just do a little example to show you how to create this Routh array. Instead of me just describing how it all works, we can just do it by example, and I think you'll see it a lot quicker. So let's say that we have some g of s that looks like this. 3s plus 1 over, let's say, 5s cubed plus 2s squared. We'll do an easy one here to get things started, and then we'll do a couple harder ones. So our characteristic equation that we extract out is this. 5s cubed plus 2s squared plus 3s plus 7. And the first thing you do is you set up those labels on the left-hand side, and you do it based on the highest, the order of that characteristic equation, highest power of s. And so typically what you do is you put the first two labels kind of right next to each other like that, and then you want to give yourself a little bit of extra room for the other labels, and you'll see why in just a minute. Now I'm going to switch around some colors here just to illustrate what happens. To fill in this first row, you key off the s cubed terms, and then you skip every other one. So basically we're doing all the odd terms in that first column. So I put a 5 there and a 3 over here. And then the next row, you key off of the s squared, because that's an s squared. So we put a 2 there and a 7 there. So now we have all the even terms. Now to fill in the rest of it, what you do is it's kind of a negative determinant, not quite, but it's that general concept. You go this way, 2 times 3, so I'll go do this in gory detail. 2 times 3 minus 5 times 7 divided by this. And so if you go through all that math, you'd get negative 29 sevenths. And I'll just circle that because I don't want to lose track that that is the element in the first row that I'm going to need to analyze. Now for this next term, what you would do is start off with this same 2, and instead of multiplying it by the 3, you go over to this column. Now there's nothing there, so we can pad it with zeros. So here what I would have is 2 times 0, 2 times 0, minus that 0 times that 5. And the interesting part is all over this 2 again. It's always divided by elements from that first column. And you go through all that, and it's pretty easy. You get 0, and I'll circle that again. That actually flows into that column. I sort of got a little bit twisted, but that's okay because I'm just about done. Now for this element, and really that's the last one we need because all I need to analyze is the first column. I go, and I'm going to switch to red now, I go negative 29 sevenths times 7. So let me write that down. Minus 0 times 2 divided by negative 29 over 7. I divide by this term again, the one right above the row that I'm working with. And when I go through all that math, I get 7, which I'll circle again. Now, to wrap this up, the analysis I need to do is of this first column. And what I see here is I have a positive 5, positive 2, a negative 29/7, so I have a sign change here. And then I go from negative 29/7 to 7, so I have another sign change. So I have two sign changes, and what that tells me is that I have two right half plane poles. The system is definitely unstable, and I know that I have two poles in the right half plane. Go ahead and use your calculator or MATLAB or something, whatever root solver you have at hand, and solve for the roots of that. And what you'll find is you have a couple poles, complex poles over here, and a pole there. So we have two of those three poles in the right half plane. Okay, so let's do another example that's just a little bit more complicated. It's actually the one that I used in that first page that we had, the little motivating description. And this example is kind of nice because, here I better call it f of s, because I have different coefficients of each of the terms in this polynomial so that we can keep them all straight as we go through the math. So here's my first two rows, s to the fourth, s cubed, and then I need to give myself a little bit of room, so I'll do an s squared, an s to the 1, and s to the 0. And so I fill in these two rows first. I have a 2 from here. Remember, these are all the even ones because I started with an s to the fourth. So I have a 2, a 5, and a 9. And then for the next row, I have a 3 from here, a 7, and 0. And now I just start doing the math. So let's see, I have 3 times 5, or 15, minus 2 times 7, or 14, over 3. And what that is 1/3. And again, I'll circle it, and I'll try to keep it under into the correct column. Now for the next term, I go 3 times 9, so I have a 27, minus 0 times 2, so minus 0, divided by this, 3, and so I get 9. And for the last one, let's see, well, I don't have anything over in this column, and I need that column to figure out what goes into this column. But I just pad it with zeros, and of course then I'd get 3 times 0 is 0, minus 2 times 0, which is 0, so I just get 0. Now moving on to the S1 row, this one right here. I'm going to be dividing through everything by this 1/3. And I start with this element, and I'll have 1/3 times 7, so 7/3, minus 9 times 3, which is 27, divided by that 1/3. So this gives, let's see, I'll sneak it in here, negative 74/3. I'll circle it. Okay, so the next element, which goes in here, is 1/3 times 0, which is 0, minus 0 times 3, which is 0, divided by 1/3, but who cares? So I have that element. And of course I'll get a 0 here too. And finally for the last row, I don't even have to do the last row, I just need this element. So I'll have negative 74/3 times 9, which is, that's a big, negative 666 over 3, minus 0 times 1/3, which is 0, divided by negative 74/3. Well, that's pretty straightforward. All I get is 9, and that'll always happen in that last element. That is, I'm going to take this quantity times something, minus 0 divided by this quantity, so I always will just get this element again. Great, so now I can analyze this column, and I can see that I have two sign changes. Let me switch colors just to make that a little easier to see. I have a sign change there and a sign change there. So again, two sign changes, and so I have two right half plane poles. Go ahead and check it. Use your root solver, check the roots of that, and that is exactly what it will tell you. Now, let's do the last example, which is how we started this set of slides, and that is with this type of an example. Let's say that we have, it's a little bit different actually than how I presented it in the first page, but this way is more interesting. So let's say I have a closed loop system that looks like this. Maybe this is my plant, and this is the controller, and it's parameterized in K. And the problem here is, what is the range of K for stability? Great question. Let's use Routh-Hurwitz. So the first thing we have to do is get the closed loop transfer function, and that would be 42K over this. This is my loop transfer function. And then I'd have 1 plus my loop transfer function again. And if I multiply everything out, I'll get 42K divided by S plus 1, S plus 2, S plus 5 plus 42K. And that's my characteristic equation. So we'd have to multiply that out, and we can easily do that. And we'll get S cubed plus 8S squared plus 17S plus 10 plus 42K. Beautiful. Now I can do the Routh-Hurwitz. My first two indices are S cubed and S squared. Give myself a wee bit of room because I do have some strange terms in there and I might need some extra room. So let's see. I get a 1 from there, and a 17 from here, an 8, and a 10 plus 42K. Now let's go through and get this S1 row. I'll have 8 times 17, that's 136, minus this times that, so that's minus 10 plus 42K, all divided by this, which is 8. Not much I can do there. To get this element, I would pad these two rows with zeros, and I'd get 8 times 0 minus 0, so I just get 0. And this looks like a 1/8, so I'm just going to erase that little line. There we go. And for my last element, I take this, multiply it by this, subtract off 0, and divide by this. So I just get, as I mentioned before, this element goes right down to there. Now, for stability, I can have no sign changes. So that means this term has to be greater than 0, and this term has to be greater than 0. I really don't care about this 8 down here, so I just grab the numerator of that and this. And so let's see, 136 minus 10, that's 126 minus 42K has to be greater than 0, and 10 plus 42K has to be greater than 0. So if we look at this one first, what this says is that 42K has to be greater than negative 10, or K has to be greater than negative 10 over 42. Great. Then we could look at this one, and what it says is that, let's see, 42K has to be less than 126, or K has to be less than 126 over 42, which is 3. Oops, that's a less than 3. Now, normally we don't work too much with negative values of K, but what this is saying is that K has to be greater than negative 10 over 42, which is back here somewhere. If this is K, this is not the complex plane anymore. This is just K. sort of a number line. So k has to be greater than negative 10 over 42, and it has to be less than 3. So k equal 3 up here somewhere. Now we really don't care too much about this one, so we're just going to focus on this. So the net result is that k has to be less than 3. Now what does this mean physically? Let me draw a complex plane. Okay. Now, if you sort of reason this out, what it's saying is that for k less than 3, my poles must be in the left half plane based on that Routh stability. When k equals 3, well, let's do k greater than 3 first. When k is greater than 3, now we know that we'll have sign changes in that first column. So that means that for k greater than 3, I have some closed loop poles over in the right half plane. And guess what happens for k equals 3? For k equals 3, I'll have some poles on the imaginary axis. And we can actually exploit that concept when we look at some special cases of the Routh array, which is the topic of another video. So just to recap, we introduced the Routh array, and the focus on it is grabbing the characteristic equation of some transfer function, creating a Routh array, and then analyzing the first column. Now just using a Routh array tells us about roots, but we could get that from a root solver. The really powerful part of the Routh array is when you use it for design or for determining the range of some parameters k, k1, k2, k3, etc. for closed loop stability. And we did some examples with that. So again, this is Gordon Parker from Michigan Tech, and thanks for watching.